to get started on circuits, we're going to go over a few things we've discussed. We have discussed, let's see, potential difference. Current and resistance. Potential difference, current and resistance, and field and charge. But these are the three concepts we've discussed so far that we'll use to help us understand circuits. We've also drawn some circuits in sort of a cartoon mode. So let me look at one. We always start with a battery, kind of like that, with a couple of terminals. And one of the terminals is positive, one is negative. And we know that EMF means that's the voltage difference created by the battery. And we do little conducting wires like this. And one thing we could connect them to is just a resistive rod of material like that with some resistivity rho. And you hook up the wires to the rod like that. And if you do that, we know what's going to happen. Current is going to flow down the wires, I'll use capital I. And inside, that means we imagine current flow as positive charges drifting with the direction of the current. We know for a conductor, it's really negative charges going the other way, etc. Let's go a few properties here. We know that the length of the wire we've been calling L, or the length of the cylinder. We know it has a cross-sectional area A is what we've been using. And that's about it. We know that this electrode would be at EMF volts plus EMF, and this would be at 0. If we wanted to set the negative electrode as 0, this would be at EMF. And we haven't really proven it yet. Maybe we have, I forget exactly what we did. But we know that basically the wires, the point of the conducting metal wires being good conductors is you get very little potential drop across them. So when you put a resistive element between these metal conducting wires, you say one side gets all of the EMF. So that's at positive EMF, and this is at 0. And you assume there's no potential drop across these perfect conducting wires. All right, that's what we drew. And then we talked about a few concepts. We talked about resistance, how to calculate the resistance of that rod. Is R, big R is resistance, it's equal to the density, or the resistivity, times the length over the area. Pretty much what you would expect. R, the resistance will increase as these two, rho and L, increase, and it'll go down as the cross-sectional area gets bigger, more places for the conductors to go. And resistance, you may recall, is in ohms. We talked about Ohm's law, and I'll put it in parentheses as we discussed. It's not really a law, but it's the relationship between the voltage difference, the potential difference you apply to this resistive element, and the current and the resistance. And of course, it's the famous, we can write delta V to remind ourselves it's the voltage across the thing equals IR. Ohm's law. Another thing around here that's worth mentioning is that often in circuits, we start to talk about the potential, the voltage drop. Like if you're doing a lab, you might call this the voltage drop. Because really, if you think about it, if you follow the current, it goes from high to low. So what is the potential difference in the way that we talked about it in our sort of field discussion? It'd be negative. If it goes from high potential to low potential, differences are always low minus high, or final minus initial. So 0 minus EMF would be the negative EMF. So often voltage drops across resistive elements are inherently negative, but that's why we call them drops. So we kind of use the language to take care of the negative. And often when we write delta V's, we're talking about magnitudes. But sometimes not, and you'll see as we go. For the next couple of lectures, I'll be talking about magnitudes. When the sign becomes important, I will let you know. Okay, but that's sort of a new name for potential difference in circuits, the voltage drop across the circuit. So if we wanted to think about what's happening in this circuit, well, since nothing really happens in the wires, there's no voltage drop across the wires, you would just say the voltage drop across the resistor is the EMF, and you could figure out how much current flows out of the battery because you just apply Ohm's law to the one element we have. The EMF equals the current flowing here, flowing everywhere and back into the battery, and the resistance that you'd calculate. There's one more quantity called the power. We haven't talked about it yet. I'm going to throw it in because it's a pretty quick concept. We might do it more formally later. But if you think about it, the charge carriers here are charges going from high potential to low potential. So they're going down in potential, and they have charge. Therefore, they're also going down in potential energy. So you can think about how much energy are you losing in this resistor, and you lose because it turns the current, or it generates heat. So you're losing electrostatic or electric potential energy, turning it into heat. So sometimes you're interested in how much. So you characterize it as a power. Since you usually have a continuous current flow, you lose so much energy per unit time. So if you remember that power from 125 is the change in the energy over the change in the time, where E is sort of the total energy. Then we would say, let's see, so what is the change in energy? Well, what you're really losing is the electric potential. So it would be Q, the charge of a charge carrier, times the delta V. So it'd be Q times how much potential drop it goes through. That's an energy. And then in how much time, delta T. And if you wanted to express this in terms of things that you talk about with circuits, you'd notice that Q over delta T is current. And how much charge goes through that per unit time, that's how we define I. So the short equation is just P equals IV, or I delta V. If we have a resistive element, or really any element, then the power being dissipated is the current times the potential drop. So just a quick intro to that one. We'll be doing more with it later. But this is all we need to get started.